Hi everyone, my name is Augusto and it's a joint work of Florian, Malte, and Guillem. And we're going to talk about listed successor generation using curve optimization techniques. So I'm going to start by showing you an example of grounding with this block word action schema. And here in this action schema, I have two parameters, x and y, and these are essentially three variables that occur both in the precondition and the effect. And in grounding, what most classical planners do, they simply replace these three variables with objects that are listed here below of the task. And then they replace the object, for example, x is replaced with block 1, then y, I don't know, block 7, and they replace that everywhere. And then we go from a first order logic representation of the action to a ground propositional representation of the action. So in this case, after grounding, would end up with something like that. We have an action stack, block 1, block 2, and have the same action or the same name of the action, but substituting the three variables with all other objects. So in this example, we have almost 10,000 ground actions, which is still fine. Almost every classical planner nowadays can handle it. But grounding does not necessarily need to always be fine. Grounding can also be the bottleneck in many of these tasks. So for example, in the organic synthesis domain, instance 11 more specifically, there are almost 71 trillion ground actions if you use a naive grounding algorithm for planning tasks. Of course, there are better algorithms than that, but they don't go much further. They still cannot handle these tasks that are that large. And even worse, if you compare the 71 trillion ground actions that it might possibly have to the optimal plan length, then things sound even worse, because with only 2 ground operators here, it's enough that we found an optimal plan in this instance 11 for organic synthesis. So most of the work in the grounding, among of the 71 trillion actions, we only would need 2 of them to already found a plan. So most of the work there is useless. So to show that grounding is really fine, if you check IPC, very few domains, grounding is very problematic. However, sometimes it may require way more effort than we actually need. And in this talk, we're going to focus on what we can do about that. And our focus here is lifted planning, and in our scenario, lifted planning, we use ground states and action schemas. And what do I mean by that? I'll explain each of these terms individually. So let's start with ground states. And in the planning task, you usually have this section of predicates or tells you the predicate symbols and the arity of them. So for example, here I have the predicate symbols at and path, and they're both binary. In the state, here I'm showing only the initial state. Basically, the state is represented as a list of things that are true. And these things are predicates, but now propositionally, which means that the three variables here were replaced with objects. And one way I can think about that is that for each predicate symbol, we could have a table. And in this table, each row of the table is the tuple that corresponds to one of these, to the objects that make one of these propositional facts true in the state. So for example, we've had at object 1 L1 in that state. Now in the table for at, we have an enters object 1 L1. And the same for path, and the same for any other predicate symbol. So essentially, our states now, our ground states represent this database where each predicate symbol corresponds to a table, and the tuples associated in this predicate correspond to entries in this database. And what I mean by action schemas then, so an action schema, we're using here the PDDL action schema, and the most tricky thing here is simply to come up with which instantiations are applicable in a given state. And if I have a precondition like that, where my precondition's conjunctive, then now that I have this view that each of the predicate symbols has its corresponding table, one way I can think about that is that this is basically a database join now. Because we have tables, and we can simply join these tables, but now naming the columns to find which instantiations are applicable in my state. Because each of these tables are the tuples that are true in my state, so the join will be all the tuples that satisfy this conjunction. And that's what we call conjunctive query. So to illustrate, if I had that now, so I had at and path as predicate symbol, but now I'm naming the columns according to the relations. So notice that these are same predicate symbols but different names, and now I just do the natural join, and at the end I have this table here, and each of these entries is one possible substitution for each of its corresponding three variables, and we know that this tuples, each entry is would generate an applicable ground action in this given state that we're evaluating. And these conjunctive queries, they are NP-hard, so they are intractable in the general case. However, there's some types of conjunctive queries that by identifying its structure, we can come up with tractable algorithms to solve them. And here I'm showing you a Sokoban case, try to illustrate the major of this island of tractability for conjunctive queries. So in the Sokoban case, basically our joiner precondition is a conjunction of these facts here. And one thing I can do is going from these facts in the precondition, I can build a hypergraph. And in this hypergraph, each free variable will be a vertex. So for example, at xy, we have two vertices, x and y here at the bottom. And each of these relations will also be a hyperedge. So at xy has an hyperedge containing these three variables. So here, the red one. The same for the blue one here, containing f, t, and y. These are the three variables, and so on and so on. And this hypergraph, we know that conjunctive query can be computed efficiently, essentially, if this hypergraph is acyclic. And if the hypergraph is acyclic, if there is what is called a join tree. And the join tree with this hypergraph is represented here. And the join tree is a tree where each node is one of these relations. And if you restrict this tree to the subtree containing only the relations containing a given free variable, then if the subtree is still connected for each free variable that you restrict, then it's still then it's in fact what you call a join tree. So for example here, for free variable f, if we restrict only to nodes containing f, so it's be the blue, the orange, and the green one, and it's still a connected subtree because we can see that there's a connection here. And if this happens for every single free variable that you restrict to, then it's a join tree. And you can try by yourself with the other ones, but I can tell you that this is already a join tree. And if a conjunctive query has a join tree, as I said, it's on a cyclic hypergraph. And the good thing is that these queries are solvable in output polynomial time. What I mean by that is the time taken to solve the query is it's polynomial in the size of its output, or basically polynomial in the size of the final relation. So no intermediate relation will have exponential, will be exponential in size based on the size of the final join relation. So this is good. And how often does this happen in planning tasks, in action schemas of planning tasks? So we check in an IPC domain, and 87% of the preconditions would have corresponding hypergraphs that are cyclic, which is good. They can be evaluated very efficiently in a given state. However, if you restrict only to hard-to-ground domains, then this number drops to 21%. And most of them is because of what I call this inequality constraints. So things saying that the object instantiating variable x should be different than the object instantiating variable y, and so on. So if we process inequalities separately, not as tables in the database, but we process them based on their built-in meaning in the PTDL syntax, then we can, the number of cyclic hypergraphs goes up to 80%, which is also good, because then it means that most of the action schemas will also be tractable in this hard-to-ground domain. And the question is, how good is performance in practice? So here I show you a comparison of these hard-to-ground domains listed on the right side between our planner and fast downward. And I'm showing you time in the case where you're running a greedy best first search with go count heuristic. And you can see that our planner is much faster in these hard-to-ground domains and even solve many more instances than fast downward. But you can also see that in this instance where this time is up to, I don't know, 10 seconds, let's say, our planner is much faster usually, and that's because it's an instance where the ground is the main bottleneck. But as the instance gets more challenging, especially for the search component, then fast downward, the grounding performance there starts paying off and the times get closer. And in fact, as the instance get harder and harder, then fast downward is already faster than our planner, essentially because the search component fast downward is faster than our search component, because we still need to perform these joins for each action schema in each state, while fast downward amortizes that with the grounding. So as the search gets harder, our planner does not pay off anymore, but for this hard to ground but easy to search domains, our planner pays off. And we also had a comparison here for the LRPG domain, LRPG planner and this state-of-the-art listed planner. And you can see that our planner is simply using this specific techniques for successor generation becomes much faster than LRPG. Here I'm compared to the full configuration of LRPG, and our planner solves way more instances, way more fast in general. So to conclude, we show that listed planning can help in this hard-to-ground domain, and especially because most of the planning tasks have action schemas with acyclic preconditions which are tractable to compute. And we also show that our planner is much faster than previous state-of-the-art listed planners. That's all I wanted to say. Thank you very much.